From nothing, everything was born. But was nothing ever truly empty? Nothing. At first glance, it seems straightforward, but defining it proves to be surprisingly complex. Our universe began from what appears to be nothing, but what does that truly mean? Is there a state of absolute nothingness, or does nothing itself have some form of hidden existence, a backdrop from which something can emerge? And where did this nothingness come from in the first place? Long before modern science tried to unravel the universe's mysteries, ancient philosophers were already pondering profound questions. What does it mean to exist? Could there ever truly be such a thing as nothing? One of the earliest and most influential thinkers to confront this paradox was Parmenides of ancient Greece. He proposed a radical idea: nothing cannot exist. To him, the very concept of nothingness was contradictory. If something genuinely did not exist, how could we even conceive of it, let alone describe it? Parmenides argued that existence has no beginning or end, it simply always was. He believed the universe was eternal, unchanging, and never created because if there had ever been a moment of absolute nothingness, how could anything have ever come into being? His perspective challenges us to reconsider our assumptions. If nothingness is truly impossible, does that imply that the universe has always existed in some form? However, not everyone agreed with Parmenides. Even in his time, other great thinkers grappled with this paradox. Aristotle, another legendary philosopher, viewed nothingness differently. He didn't see it as a contradiction but as a kind of potential, a blank canvas from which new things could emerge. Imagine an empty canvas before an artist begins to paint. For Aristotle, this emptiness was not truly nothing but a space full of possibilities, a foundation for creation. He believed that even if a space seemed empty, it still held the potential for existence. For centuries, philosophers and scientists have debated these ideas. Can absolute nothingness exist? If the universe originated from nothing, what kind of nothing are we talking about? These questions challenge the boundaries of human thought and force us to rethink everything we believe about reality itself. In more recent times, thinkers like Immanuel Kant began exploring the limits of human understanding. He posed a profound question: could absolute nothingness, the complete absence of everything, be something beyond our mental grasp? Our entire existence is shaped by a world full of matter, space, and time, things we can touch, see, and measure. But Kant argued that true nothingness, where absolutely nothing exists, is beyond our imagination or comprehension. It's a concept so foreign to our daily experiences that it feels out of place in our understanding of reality. This leads us to a deeper question: could it be that absolute nothingness doesn't actually exist? Or is it possible that what we perceive as nothing is, in fact, the source of everything around us, the spark that ignites creation? These are the questions that have puzzled humanity's greatest minds throughout history, leading to one of the most profound mysteries of all, the birth of the universe. Fast forward a few thousand years, and our understanding of nothingness has evolved dramatically. While philosophers pondered these deep and complex questions, scientists quietly worked in the background, using mathematics and experiments to uncover the universe's secrets. And this is where the story becomes even more fascinating. For centuries, scientists believed that space, the vast expanse where nothing seemed to exist, was exactly that, nothing. A vacuum was thought to be a void, an emptiness devoid of matter or energy. But in the 20th century, this perspective was turned on its head by the revolutionary work of Albert Einstein. His theory of general relativity showed that space and time were not separate entities but interconnected, forming a flexible fabric that could bend and stretch in response to mass and energy. This was a groundbreaking idea. It revealed that space wasn't just a passive stage where events unfolded but an active, dynamic participant in the universe's unfolding drama. The real revolution in our understanding of nothingness came with the advent of quantum mechanics, a branch of physics exploring the smallest building blocks of reality. Quantum mechanics revealed a bizarre truth: even in the emptiest parts of space, where nothing appears to exist, there is still activity. Imagine a perfect vacuum, a space devoid of matter, light, or any detectable presence. Even in this seemingly empty void, something extraordinary is happening. Tiny bursts of energy spontaneously pop into existence and vanish just as quickly. These fleeting events are known as quantum fluctuations, minuscule, rapid fluctuations of energy that appear and disappear in the blink of an eye. It's as if the universe is constantly buzzing with activity, even in the voids where nothing seems to be. These fluctuations are so fast and tiny that they are invisible to the naked eye, yet their effects can be measured. It turns out that even in seemingly empty space, invisible fields are at work, constantly fluctuating like ripples on the surface of an ocean, creating virtual particles that appear and vanish almost instantly. This astonishing discovery challenges our understanding of nothingness. If even the emptiest space is alive with potential energy and quantum activity, then is it really empty? Could these constant fluctuations be the key to the birth of everything? Is it possible that the entire universe emerged from one of these quantum fluctuations, a burst of energy that expanded into the vast cosmos we see today? This mind-bending idea forms the foundation of modern cosmology. If quantum fluctuations can create tiny bursts of energy in a vacuum, could they also explain how the universe itself could arise from what appears to be nothing? This challenges our deepest assumptions about nothingness and existence. The concept of nothingness has fascinated humanity for centuries, from the ancient philosophers who pondered its meaning to modern scientists uncovering its complexities. Once seen as a lifeless void, we now understand that even the most seemingly empty space is teeming with potential. The quantum world reveals a reality where nothingness is alive with fluctuations, possibilities, and energy waiting to burst into existence. While science and philosophy have given us incredible insights, the true nature of nothingness remains a profound mystery. But this very mystery is what makes the universe, and our place within it, so extraordinary and captivating. Perhaps the greatest story ever told is the one that begins with nothing, leading to everything we see around us. Smallest fraction of a second, the universe expanded from a point smaller than an atom to something billions of times larger. This expansion didn't occur in a specific direction, instead, space itself stretched, carrying everything within it. The Big Bang marked the birth of time, space, and all that exists, but that was merely the beginning. The real mystery lies in what happened next. How did that initial burst of energy, this extraordinary explosion of space, transform into galaxies, stars, planets, and all the components of the universe as we see it today? To unravel this, we need to delve into the timeline of events that followed the Big Bang, examining each critical moment that shaped our cosmos. From the universe's very first moments, cooling processes began to take effect. Clouds of gas formed, stars ignited, and galaxies started to take shape, each one a colossal collection of stars and matter drifting through the ever-expanding universe. Over billions of years, these stars and galaxies evolved, creating the intricate and diverse cosmos we witness now. The transformation from an unimaginably tiny, hot point to the vast, complex universe we inhabit today is one of the most astonishing stories ever told. To truly grasp how the universe evolved, we need to break down these events moment by moment, examining the tiniest fractions of a second. In the early universe, monumental changes occurred in almost no time at all. Understanding these brief yet extraordinary moments is crucial to comprehending how everything began. Let's start at the very beginning, during the Planck epoch. This was a period so early in the universe's history that it defies our imagination, occurring less than a trillionth of a second after the Big Bang. The universe was then incredibly small and unimaginably hot, with temperatures exceeding a quadrillion degrees. In this extreme environment, the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single force. This unification is something we struggle to fully understand because, in today's universe, these forces operate independently. But during the Planck epoch, they were merged into one. What does this mean? Essentially, everything we know about physics, all the laws that govern the universe, were condensed into a single, unified force. However, This era remains a profound mystery. Our current physical theories, including Einstein's general relativity and quantum mechanics, fail to describe what happened under such extreme conditions. It is as if we are trying to assemble two puzzles whose pieces simply do not fit together. During this time, the universe expanded at an extraordinary rate. Space itself seemed to stretch at a speed beyond comprehension. However, the universe was so hot and dense that light could not travel freely. Everything was shrouded in a kind of cosmic fog, preventing us from directly observing this early period. As the universe continued to cool, though it was still millions of times hotter than the core of the Sun, significant changes occurred. The first major shift was the separation of gravity from the other three forces. This marked the beginning of what is known as the Grand Unification Epoch. During this era, electromagnetism, along with the strong and weak nuclear forces, remained unified while gravity started to act independently. Then came an event that transformed everything: inflation. This explosive phase of rapid expansion occurred about 1/septillionth of a second after the Big Bang. Unlike anything before, inflation caused the universe to expand faster than the speed of light. While this might sound impossible, it is important to remember that it wasn't matter moving through space at this speed, it was space itself expanding. This rapid inflation stretched the universe from subatomic scales to macroscopic sizes almost instantly. Imagine something growing from smaller than an atom to billions of times larger in a blink of an eye. It is nearly impossible to fathom, yet this is precisely what scientists believe happened. Why did inflation occur? The exact cause remains uncertain, but many scientists theorize it was driven by a special form of energy known as the inflaton field. This energy created an immense pressure, forcing space to expand at a breakneck pace. As the universe expanded, it also cooled, leading to the separation of the remaining fundamental forces. As temperatures dropped further, particles began to form. The universe entered the quark epoch, where quarks and gluons, the building blocks of protons and neutrons, came into existence. However, conditions were still too extreme for stable matter to form. Instead, the universe resembled a chaotic cosmic soup where particles continuously collided, appeared, and vanished. With continued cooling, particles started to bind together, leading to the formation of protons and neutrons. Around 10 seconds after the Big Bang, photons, particles of light, began to play a critical role. The universe was still filled with free electrons and protons, creating an opaque fog that trapped light. However, as the first atomic nuclei formed through nucleosynthesis, primarily hydrogen, helium, and a bit of lithium, the universe began to transition from chaos to structure. Hundreds of thousands of years later, the universe cooled enough for electrons to combine with protons, forming neutral atoms. This phase, known as the era of recombination, was a turning point. The once opaque universe became transparent, allowing light to travel freely for the first time. This moment left a profound mark on the cosmos, the cosmic microwave background, CMB, radiation. The CMB is the faint glow of heat left over from the Big Bang. It serves as a cosmic echo, allowing scientists to peer back in time to when the universe was only 380,000 years old. This afterglow provides critical evidence of the universe's origins and supports the Big Bang theory. But how do we know all of this for certain? The Big Bang theory is not merely a wild guess. It is grounded in strong evidence, including the uniformity of the CMB across the sky, which indicates that the universe began from a single, incredibly hot point. Another crucial piece of evidence is the redshift of distant galaxies. When we observe galaxies far from us, their light appears stretched toward the red end of the spectrum. This redshift occurs because the universe is expanding, and as space stretches, so does the light traveling through it. Discovered by Edwin Hubble in the 1920s, this phenomenon shows that galaxies are moving away from us, confirming that the universe is still expanding. Finally, the abundance of light elements such as hydrogen, helium, and lithium also supports the Big Bang theory. These elements formed during the early stages of the universe, and their proportions match predictions made by models of the early universe. Together, these pieces of evidence paint a coherent picture of a universe that began with a bang, a moment of creation from which everything we see today emerged. From the smallest particles to the largest galaxies, all of existence shares a common origin in that singular, mind-bending event. The story of the universe's birth and evolution is a journey through time and space, from the first moments of existence to the breathtaking complexity we observe now. And while we have uncovered many of its secrets, the universe still holds countless mysteries, inviting us to continue exploring the nature of reality itself. Furnaces, forging the heavier elements that make up everything around us today. But at this early stage, the universe was a vast, dark expanse of hydrogen and helium gas. So, how did it transform from this simple state into the magnificent cosmos we observe now, filled with galaxies, stars, planets, and life itself? The answer lies in the force of gravity. Even in the early universe, slight differences in the density of matter existed. These tiny fluctuations, left over from the rapid expansion during inflation, caused some regions to have slightly more mass than others. Due to gravity, these denser areas began to attract more matter, gradually growing larger and denser over time. This process of gravitational collapse continued for millions of years. As hydrogen and helium atoms were pulled together, they formed massive clouds of gas, growing denser and hotter at their centers. Eventually, the pressure and temperature became so intense that nuclear fusion was triggered, the same process that powers our sun. These first stars were unlike any stars we see today. They were gigantic, hundreds of times more massive than our sun, and burned through their fuel quickly, shining with a brilliant but short-lived intensity. These ancient stars, known as population 3 stars, were composed almost entirely of hydrogen and helium, as no heavier elements existed yet. But these colossal stars did not last long. After a few million years, they exhausted their nuclear fuel and exploded in titanic supernovae. These explosions were not just spectacular cosmic fireworks, they were the universe's first alchemical forges. In the intense heat and pressure of these supernovae, the first heavy elements were created: carbon, oxygen, iron, and all the building blocks of planets and life. These newly formed elements were scattered across the universe by the powerful blasts of the supernovae, enriching the surrounding clouds of gas and dust. This cosmic recycling process paved the way for the formation of the next generation of stars and the first galaxies. Gravity continued to work its magic, pulling together clouds of gas and dust, which began to spin and collapse into new stars. Some of these stars grouped together, forming the first primitive galaxies. These early galaxies were smaller and more chaotic than the majestic spiral galaxies we see today, but they were the first structures in the young universe. As more stars were born and died in supernovae, heavier and more complex elements accumulated. This ongoing cycle of star formation and destruction enriched the cosmos, making it possible for planets, moons, and eventually life to form. Among these newly forming stars, our own Sun was born around 4.6 billion years ago, in a swirling cloud of gas and dust left over from countless previous generations of stars. The remaining material around the young Sun began to clump together, forming the planets, moons, asteroids, and comets of our solar system. Earth, one of these newly formed planets, was just a molten ball of rock at first. But over millions of years, it cooled and developed an atmosphere, oceans, and the complex chemistry needed for life. And here we are today, on a small blue planet orbiting a medium-sized star, in one of the billions of galaxies that make up the universe, all of it tracing back to that tiny, hot point of energy at the beginning of time. This is the incredible story of how everything, planets, stars, galaxies, and even life itself, came to be. It's a tale of transformation from simple particles to the complex, beautiful cosmos we observe today. And it all began with the Big Bang, an event that set everything in motion and continues to shape our universe as it expands ever outward. But as remarkable as this story is, it also raises even more profound questions. What lies beyond our observable universe? Will the universe continue expanding forever, or will it eventually collapse back into itself in a big crunch? Could there be other universes, other realities beyond our own? To explore these questions, we must dive deeper into the mysteries of dark matter and dark energy, two invisible forces that make up most of the cosmos yet remain largely unknown. We must also continue our quest to understand the nature of singularities, black holes, and the very fabric of space and time itself. Our journey to understand the universe is far from over. Every new discovery brings us closer to understanding the grand cosmic puzzle, yet also reveals just how much we have yet to learn. As we gaze up at the night sky, we are reminded that the story of the universe is still unfolding, and our quest for knowledge is just beginning. The universe began as a tiny point of unimaginable energy and has grown into a vast, complex cosmos teeming with stars, galaxies, and life. From the simplest particles to the most intricate structures, everything around us is a product of cosmic evolution, driven by the forces of gravity, nuclear fusion, and the endless dance of matter and energy. And as we continue to explore the stars, to peer back in time through powerful telescopes, and to unlock the secrets of quantum mechanics and relativity, we are not just learning about the cosmos, we are discovering our place within it. The universe is a grand and beautiful mystery, a story of creation and transformation that began with the Big Bang and continues to this day. And as long as we keep asking questions, keep searching for answers, the story will never truly end. The core becomes hot and dense enough to fuse hydrogen atoms into helium. This nuclear fusion releases an immense amount of energy in the form of light and heat, counteracting the force of gravity that is trying to collapse the star even further. A delicate balance is reached between the inward pull of gravity and the outward pressure from the fusion reactions, and the star enters the longest and most stable phase of its life, the main sequence. During this phase, a star shines steadily, converting hydrogen into helium in its core and radiating light and heat into space. This is the period when stars, including our own Sun, spend the majority of their lifetimes, sometimes billions of years. The size and brightness of a star depend on its initial mass. Smaller stars burn their fuel slowly and live longer, while massive stars burn through their hydrogen rapidly, shining brighter but living shorter lives. As a star ages, the hydrogen in its core gradually runs out. With no more hydrogen to fuse, the balance between gravity and pressure is disrupted. Gravity begins to take over, compressing the core even further and raising the temperature to extreme levels. When this happens, a new phase of fusion begins. Helium nuclei start to fuse into heavier elements like carbon and oxygen. This new wave of fusion releases even more energy, causing the outer layers of the star to expand dramatically. The star swells into a red giant or, if it's massive enough, a supergiant. These colossal, bloated stars shine with a reddish hue, and their outer layers are stretched far away from the core. Meanwhile, in the core, heavier and heavier elements are forged through fusion, elements like neon, magnesium, silicon, and eventually iron. Iron is the end of the line for fusion. Unlike lighter elements, fusing iron doesn't release energy, instead, it absorbs it. Once a star's core is primarily composed of iron, fusion stops abruptly. Without the outward pressure to counteract gravity, the core collapses in on itself with unimaginable force. In smaller stars, like our Sun, this collapse is relatively gentle. The outer layers are shed into space, creating a beautiful shell of glowing gas known as a planetary nebula. What remains is a dense, hot core called a white dwarf, which slowly cools over billions of years, fading into darkness. But for massive stars, the story is far more dramatic. The core collapses so violently that it triggers an enormous explosion, a supernova. This cataclysmic event is one of the most powerful forces in the universe, outshining entire galaxies for a brief period. In the intense heat and pressure of a supernova, even heavier elements like gold, silver, and uranium are created, enriching the cosmos with the building blocks of planets and life. The remnants of these colossal explosions vary depending on the star's original mass. If the core is between about 1.4 and 3 times the mass of our Sun, it becomes a neutron star, a city-sized object so dense that a teaspoon of its matter would weigh billions of tons. Neutron stars are incredibly magnetic and can spin at astonishing speeds, emitting beams of radiation as pulsars. But if the original star was even more massive, the core continues to collapse under its own gravity, forming a black hole, a region of space where gravity is so strong that not even light can escape. Black holes are among the most mysterious and powerful objects in the universe, warping space and time around them. These stellar deaths are not merely spectacular cosmic events, they are essential for creation. When a supernova explodes, it scatters heavy elements across space, seeding future generations of stars, planets, and even life itself. The oxygen we breathe, the calcium in our bones, the iron in our blood, all were forged in the hearts of ancient stars and spread across the cosmos by supernovae. This cosmic recycling continues today. As clouds of gas and dust enriched by past supernovae collapse under gravity, they form new stars and planetary systems. Our own solar system was born from one such cloud approximately 4.6 billion years ago, a cloud enriched by countless generations of stars before it. Within this cloud, the Sun formed at the center, surrounded by a rotating disk of dust and gas. Over time, particles in this disk collided and stuck together, forming larger and larger clumps. These clumps grew into planetesimals, which eventually merged to form the planets, moons, asteroids, and comets of our solar system. Earth, one of these young planets, began as a hot, molten sphere. But as it cooled, an atmosphere formed, rain fell, and oceans appeared. Complex chemistry followed, setting the stage for the emergence of life. From the simplest microbes to the rich diversity of plants and animals, life evolved, powered by the energy of a nearby star. The Sun stars, therefore, are not just twinkling points of light in the night sky, they are cosmic engines of creation. They forge the elements necessary for life and distribute them across the universe through supernova explosions. Stars shape galaxies, influence planetary systems, and even affect the potential for life on other worlds. But the story doesn't end here. The universe is still evolving. Galaxies continue to collide and merge, forming new stars. Black holes grow larger, feeding on surrounding matter and merging with other black holes. And somewhere in the cosmos, the next generation of stars and planets is being born, perhaps even a world capable of supporting life. As we look up at the night sky, we are not merely seeing distant stars, we are witnessing the history of the universe itself. Every point of light is a reminder of the cosmic cycle of birth, life, and death that has been unfolding for billions of years. It is a story written in the language of light and matter, energy and time, a story that connects us to the stars themselves. The atoms in our bodies were forged in ancient stars that lived and died long before our Sun was born. We are, quite literally, made of stardust. This realization not only deepens our understanding of the cosmos but also our connection to it. The universe is a vast and complex web of energy, matter, and time, constantly evolving and changing. From the fiery birth of the first stars to the quiet fading of white dwarfs, from the violent explosions of supernovae to the mysterious depths of black holes, the cosmos is alive with creation and destruction. And as long as we continue to explore the stars, to seek answers to the deepest questions of existence, the story of the universe will continue to unfold, one discovery at a time. Incredible force, releasing an immense amount of energy and scattering heavy elements across the universe. These elements, created in the intense heat and pressure of the supernova, include carbon, oxygen, iron, gold, and even uranium. Without these explosions, the universe would be a much simpler place, devoid of the complex chemistry needed to form planets, oceans, and life itself. Supernovae are not just dramatic endings, they are also beginnings. The shockwaves from these cosmic blasts can travel across space, colliding with nearby gas and dust clouds. This collision compresses the gas, triggering the birth of new stars. In this way, supernovae help recycle matter, enriching the universe with the heavy elements necessary for life. But the story of a massive star's death doesn't end with the explosion. What remains after the outer layers are blown away depends on the mass of the core. If the core is between 1.4 and 3 times the mass of the Sun, it becomes a neutron star. These are incredibly dense objects made almost entirely of neutrons. A neutron star is so compact that a teaspoon of its material would weigh billions of tons. Neutron stars are not just dense, they are also magnetic powerhouses. Some neutron stars spin rapidly, emitting beams of radiation from their magnetic poles. If these beams are pointed toward Earth, we observe them as pulses of light, which is why they are called pulsars. Pulsars rotate with such precision that they rival atomic clocks, making them valuable tools for astronomers. However, if the core is even more massive, greater than 3 times the mass of the Sun, gravity wins the battle completely, and the core collapses into a black hole. A black hole is a region of space where gravity is so strong that nothing, not even light, can escape. It is an object of infinite density and zero volume, creating a point known as a singularity. Around this singularity is the event horizon, the point of no return beyond which nothing can escape the gravitational pull. Black holes are among the most mysterious objects in the universe. They warp space and time around them, distorting everything that passes nearby. Anything that crosses the event horizon is lost forever, adding to the black hole's mass. Black holes can grow by feeding on surrounding gas and stars, becoming even more massive over time. At the centers of most galaxies, including our own Milky Way, lie supermassive black holes with masses millions or even billions of times greater than the Sun. These cosmic giants are thought to play a crucial role in the formation and evolution of galaxies. As they consume matter, they release enormous amounts of energy, shaping the galaxies around them. The deaths of massive stars, through supernovae and black holes, are cataclysmic events that reshape the universe. They create the heavy elements that make planets and life possible, and they trigger the birth of new stars and solar systems. Without them, the universe would be a much simpler and lifeless place. But the life cycle of stars is not just about death and destruction, it's also about renewal and creation. The gas and dust ejected from dying stars are recycled into new generations of stars and planets. This cosmic recycling has been going on for billions of years, creating a universe rich in complexity and diversity. Our own Sun is part of this grand cycle. It was born from a cloud of gas and dust enriched by earlier generations of stars. Around 4.6 billion years ago, this cloud collapsed under gravity, forming the Sun at its center. The remaining material flattened into a rotating disk, from which the planets, moons, asteroids, and comets of our solar system formed. Earth, one of these newborn planets, began as a molten ball of rock. Over millions of years, it cooled, developed an atmosphere, and accumulated oceans, setting the stage for the emergence of life. The elements that make up our bodies, carbon, oxygen, nitrogen, and iron, were forged in ancient stars that lived and died long before the Sun was born. We are, quite literally, made of stardust. Every atom in our bodies was created in the hearts of dying stars and scattered across the cosmos by supernovae. This profound connection to the universe unites us with the stars, the galaxies, and the cosmos itself. The life cycle of stars, from birth in stellar nurseries to death in supernovae or collapse into black holes, is a continuous process of creation and transformation. It is a story of balance and change, of destruction and rebirth, that shapes the universe and makes life possible. Stars are the engines of the universe. They forge the elements, light up the galaxies, and create the conditions for life. And even in death, they continue to shape the cosmos, spreading their enriched materials across space to create new stars and worlds. As we look up at the night sky, we are not just seeing stars, we are witnessing the history of the universe itself. Every point of light is a reminder of the cosmic cycle of birth, life, and death that has been unfolding for billions of years. It is a story written in the language of light and matter, energy and time, a story that connects us to the stars and the universe as a whole. The cosmos is alive with creation and destruction. From the fiery birth of stars to the explosive deaths of supernovae, from the quiet fading of white dwarfs to the mysterious depths of black holes, the universe is a vast and complex web of energy and matter, constantly evolving and changing. And as long as we continue to explore the stars, to seek answers to the deepest questions of existence, the story of the universe will continue to unfold, one discovery at a time. Like stars and planets. Dark matter, however, does not interact with electromagnetic forces, which means it cannot emit light, heat, or radiation. Without a way to lose energy, dark matter particles remain in fast, random motions, preventing them from clumping together to form dense structures. Instead of forming objects like stars, dark matter exists as large, diffuse halos surrounding galaxies, contributing to their gravitational mass but not participating in normal matter interactions. Additionally, dark matter does not interact strongly with itself. Unlike regular matter, which can collide and stick together, dark matter particles pass through each other and normal matter almost without resistance. This lack of interaction further prevents dark matter from forming compact objects. The inability of dark matter to cool and clump also has profound implications for the formation of galaxies and large-scale structures in the universe. While normal matter can collapse into stars and galaxies, dark matter forms a vast, invisible scaffold around which galaxies can form. The gravitational pull of dark matter draws in regular matter, allowing galaxies to develop within these dark matter halos. The cosmic web, a large-scale structure of the universe, is also influenced by dark matter. This web consists of vast filaments of galaxies connected by threads of dark matter, with enormous voids in between. The distribution of dark matter helps shape this structure, guiding the formation of galaxies and clusters along these filaments. Despite its elusiveness, the effects of dark matter are evident through gravitational lensing. When a massive object like a galaxy cluster lies between a distant light source and an observer, its gravity bends the light, distorting the image of the source. By studying these distortions, scientists can map the distribution of dark matter, revealing its presence even though it is invisible. Experiments to detect dark matter directly are ongoing. These include attempting to observe dark matter particles interacting with normal matter in underground detectors, searching for dark matter particles in high-energy collisions at particle accelerators, and looking for evidence of dark matter particles annihilating each other in space. However, no definitive detection has yet been made. The search for dark matter is one of the most significant challenges in modern physics. Solving this mystery could lead to a deeper understanding of the universe's composition, the nature of gravity, and possibly reveal new particles and forces of nature. In the grand scheme of the universe, dark matter plays a vital role. It affects the rotation of galaxies, the formation of large-scale structures, and the behavior of the universe on the grandest scales. Yet, it remains one of the biggest enigmas of our time, an unseen but essential player in the cosmic story. As we continue to explore the universe, through telescopes, particle detectors, and advanced simulations, we edge closer to unraveling the mystery of dark matter. Each discovery, whether it supports or challenges our current theories, brings us closer to a deeper and more complete understanding of the cosmos. Lensing patterns that matched predictions made by modified Newtonian dynamics, (MOND). However, these successes are exceptions rather than the rule. Most alternative theories struggle to account for the full range of evidence supporting dark matter, such as cosmic microwave background radiation, galaxy rotation curves, and the large-scale structure of the universe. One of the most prominent alternatives to dark matter is MOND, which was proposed by physicist Mordechai Milgram in the 1980s. MOND modifies Newton's laws of motion to explain galaxy rotation curves without requiring dark matter. According to MOND, at extremely low accelerations, like those found at the outer edges of galaxies, gravity behaves differently than predicted by Newton or Einstein. This modification successfully explains the flat rotation curves observed in galaxies. However, Mond struggles to explain other phenomena, such as gravitational lensing and the distribution of dark matter in galaxy clusters. A more recent extension of Mond is called TeVis, tensor vector scalar gravity, proposed by Jacob Bekenstein. TeVis is a relativistic version of Mond that attempts to reconcile the theory with general relativity. It introduces additional fields to modify gravity at large scales, preserving the successes of Mond while aiming to explain gravitational lensing. Despite some promising results, TeVis is complex and introduces new parameters, leading to questions about its simplicity compared to the dark matter hypothesis. Another alternative is F.R. gravity, which modifies Einstein's general relativity by altering the function that describes the relationship between spacetime curvature and matter. This approach can produce effects similar to dark matter on galactic and cosmic scales. However, F.R. gravity introduces additional complications and has difficulty matching observations of the cosmic microwave background and galaxy clustering. Negative mass theories propose that the universe contains particles with negative mass, which would repel regular matter. These particles would create gravitational effects similar to dark matter. However, negative mass is a highly speculative concept that contradicts known physics and has not been observed experimentally. Dark fluid theory suggests that dark matter and dark energy are two aspects of a single substance, which behaves like dark matter in galaxies and like dark energy on cosmic scales. This theory attempts to unify the explanation for both phenomena but remains largely theoretical without strong observational support. Entropic gravity, proposed by Eric Verland, suggests that gravity is an emergent phenomenon arising from the thermodynamics of information stored in spacetime. This approach explains galaxy rotation curves without dark matter by modifying the behavior of gravity at large scales. While intriguing, entropic gravity is still in development and faces challenges in explaining galaxy clusters and the cosmic microwave background. While these alternative theories are imaginative and provide novel insights into gravity and cosmology, they face significant challenges. They must not only explain the observations attributed to dark matter but also remain consistent with the well-tested predictions of general relativity and quantum mechanics. Most of these alternatives fail to fully account for all the evidence, including the cosmic microwave background, gravitational lensing, and the large-scale structure of the universe. Meanwhile, the dark matter hypothesis remains the most widely accepted explanation for the unseen mass influencing galaxies and cosmic structures. It is supported by a wide range of observations, including galaxy rotation curves that remain flat at large distances from the center, gravitational lensing that reveals more mass than can be accounted for by visible matter, the cosmic microwave background, which shows patterns consistent with the influence of dark matter on early universe density fluctuations, the distribution of galaxies and the formation of cosmic structures, which require the gravitational pull of dark matter. The search for dark matter continues with increasingly sophisticated experiments. Direct detection experiments seek to observe dark matter particles interacting with normal matter in underground detectors. Indirect detection looks for signals of dark matter annihilation or decay in space, such as gamma rays or neutrinos. Particle accelerators like the Large Hadron Collider aim to produce dark matter particles in high-energy collisions. Despite the lack of direct detection so far, the consistency of the dark matter hypothesis across multiple lines of evidence makes it the leading explanation for the missing mass in the universe. The search for dark matter is one of the most exciting frontiers in physics, with the potential to reveal entirely new particles and forces of nature. In the grand tapestry of the universe, dark matter remains an invisible but essential thread. It shapes galaxies, guides cosmic structures, and holds the key to understanding the full composition of the cosmos. As we continue to explore the universe with advanced telescopes, detectors, and particle accelerators, we move closer to solving one of the greatest mysteries of modern science, the true nature of dark matter. The mystery of dark energy, unraveling the universe's accelerating expansion. Dark energy is one of the most enigmatic and influential forces in the universe. It is responsible for the accelerated expansion of the cosmos, making up approximately 68% of the universe's total energy content. In contrast, dark matter accounts for about 26%, and regular matter, the atoms that form stars, planets, and all visible objects, comprises just 5%. This mysterious form of energy is uniformly distributed across space, exerting a repulsive force that counteracts the gravitational pull of matter. Discovery and evidence of dark energy. The existence of dark energy was first suggested in 1998 when astronomers studying distant Type Ia supernovae noticed that they were dimmer than expected. This implied that the universe's expansion was speeding up, rather than slowing down as previously believed. The discovery was a major breakthrough, leading to a paradigm shift in cosmology. Since then, multiple lines of evidence have confirmed the existence of dark energy. 1. Type Ia supernova observations. These standard candles have a known intrinsic brightness, allowing precise measurements of their distance and redshift. Comparing the observed brightness with redshift data revealed that the universe's expansion rate is increasing over time. 2. Cosmic microwave background, CMB, radiation. Tiny temperature fluctuations in the CMB, as measured by the WMAP and Planck satellites, indicate that the universe is flat. This geometric flatness implies the presence of a significant amount of dark energy. 3. Large-scale structure of the universe. The distribution of galaxies and galaxy clusters provides indirect evidence of dark energy's influence on cosmic expansion. 4. Baryon acoustic oscillations, BAO. These are density fluctuations in the early universe that left imprints on the large-scale structure. BAO measurements, combined with CMB data, support the existence of dark energy. 5. Gravitational lensing. The bending of light by massive objects also offers clues about the distribution of dark energy in the universe. Theories explaining dark energy. Despite overwhelming evidence for dark energy's existence, its nature remains a profound mystery. Several competing theories aim to explain its origin and properties. 1. Cosmological constant, lambda, proposed by Einstein and later abandoned before being revived in modern cosmology. The cosmological constant represents a constant energy density filling space uniformly. It is the simplest explanation for dark energy, corresponding to a form of vacuum energy that exerts negative pressure, driving the universe's accelerated expansion. 2. 3. Vacuum energy, quantum fluctuations. In quantum field theory, empty space is not truly empty but filled with virtual particles popping in and out of existence. This vacuum energy contributes to the cosmological constant. However, the predicted value from quantum physics is vastly larger than what is observed, leading to the infamous cosmological constant problem. 4. 5. Scalar fields, quintessence and moduli. Unlike the constant vacuum energy, scalar fields can vary over time and space. Quintessence is a dynamic field that changes as the universe expands, offering a more flexible model than the cosmological constant. 6. 7. Interacting dark energy. This theory proposes that dark energy interacts with other cosmic components, such as dark matter or gravity, influencing the universe's expansion in complex ways. 8. 9. Modified gravity theories. 10. 1. F. Gravity alters Einstein's general relativity by modifying the relationship between spacetime curvature and matter. 2. Entropic gravity suggests gravity is an emergent phenomenon linked to thermodynamic principles, potentially explaining dark energy's effects. 3. Brain world models, inspired by string theory. These models propose that our universe is a brain floating in a higher dimensional space. Dark energy could be a result of interactions with these extra dimensions. 11. Cosmological coupling. This speculative idea suggests that dark energy is linked to the expansion of space itself, with its properties evolving as the universe grows. 12. Challenges and unresolved questions. Despite the success of the lambda CDM, lambda cold dark matter, model, which includes the cosmological constant as dark energy, there are several challenges and open questions. Cosmological constant problem. The discrepancy between the observed value of the cosmological constant and the value predicted by quantum field theory is one of the greatest unsolved problems in physics. Hubble tension. There is a persistent discrepancy between the Hubble constant, the rate of the universe's expansion, measured from the CMB and from type Ia supernovae. This tension may hint at new physics or a better understanding of dark energy. Time-varying dark energy. Some observations suggest that dark energy's influence might have changed over time, possibly supporting the idea of dynamic scalar fields like quintessence. Future prospects and observations. Ongoing and upcoming observational missions aim to shed more light on dark energy's nature. Euclid Space Telescope, ESA, designed to map the geometry of the dark universe, helping to constrain dark energy models. Vera C. Rubin Observatory will conduct deep sky surveys to study dark energy through supernovae, BAO, and gravitational lensing. Nancy Grace Roman Space Telescope, NASA, will provide high-precision measurements of cosmic expansion and dark energy's effects. Conclusion. The quest continues. Dark energy remains one of the most profound mysteries in modern cosmology. Its discovery revolutionized our understanding of the universe, leading to the realization that we know very little about the majority of its contents. Whether it is a cosmological constant, a dynamic scalar field, a manifestation of modified gravity, or something entirely new, solving the mystery of dark energy will likely require a paradigm shift in physics. As astronomers and physicists continue to explore the cosmos with increasingly advanced tools and techniques, we move closer to unveiling the true nature of dark energy. Whatever the answer, it will not only reshape our understanding of the universe but also provide deeper insights into the fundamental laws of nature itself. The expanding universe. Unraveling the mystery of dark energy. The universe's expansion has fascinated scientists for decades. Recent measurements using innovative techniques have revealed that galaxies up to 2 billion parsecs away show evidence of the universe expanding faster over time. This accelerating expansion is one of the strongest pieces of evidence for the existence of dark energy, a mysterious force that makes up approximately 68% of the universe. The need for dark energy in a flat universe. Observations indicate that the universe is flat, meaning its total energy density is precisely balanced between gravitational collapse and endless expansion. However, regular, baryonic, matter and dark matter combined only account for about 30% of the needed energy. The remaining 70% must come from an unknown source, what we call dark energy. Early data from the Wilkinson Microwave Anisotropy Probe, WMAP, suggested that dark energy made up 72.8% of the universe, but more precise measurements from the Planck spacecraft have refined this to 68.3%, with dark matter at 26.8% and regular matter at just 4.9%. Cosmic microwave background and the ISW effect. The integrated Sachs-Wolf (ISW) effect provides further evidence for dark energy. When photons from the cosmic microwave background, CMB, travel through large-scale structures like galaxy clusters or voids, they gain or lose energy, creating distinct hot and cold spots in the background radiation. This effect aligns well with the presence of dark energy influencing the universe's structure and expansion. New methods to measure dark energy. Scientists have developed innovative methods to study dark energy, including using the Hubble constant to track the universe's expansion over time. By analyzing passively evolving galaxies as cosmic clocks, researchers can measure their ages and redshifts to directly estimate how fast the universe expanded at different points in its history. The mystery of dark energy, what could it be? Despite mounting evidence for dark energy's influence, its true nature remains elusive. The simplest theory is that dark energy is a fundamental property of space itself, often described as vacuum energy. According to this idea, empty space is not truly empty but filled with a type of energy that affects the universe's expansion. This concept aligns with the cosmological constant, denoted by the Greek letter lambda, a term introduced by Einstein in his general theory of relativity. However, a major problem arises with this theory. Quantum physics predicts an enormous amount of vacuum energy, 120 orders of magnitude more than what we observe. If this prediction were accurate, the universe would have expanded so rapidly that galaxies, stars, and planets could never have formed. The fact that the universe exists as it does suggests that most of this vacuum energy is somehow cancelled out, but scientists do not yet understand why. Alternative theories, quintessence and beyond. Not all physicists believe dark energy is a constant force. Some propose it could be a dynamic, evolving energy field known as quintessence. Unlike the cosmological constant, quintessence can change over time and space, acting like a field that influences the universe's expansion in a more complex way. This theory allows for dark energy to vary, potentially explaining why it became dominant in the current era of cosmic history. Phantom energy and the Big Rip. Some extreme quintessence models predict even stranger scenarios. Phantom energy, for instance, could increase over time, eventually tearing apart galaxies, stars, planets, and even atoms in a dramatic event called the Big Rip. K-essence. Another theory, K-essence, involves unusual forms of energy that could have negative kinetic energy, leading to unpredictable effects on the evolution of the cosmos. The Hubble tension and the future of dark energy research. A recent challenge in cosmology is the Hubble tension, a discrepancy in the measurements of the universe's expansion rate. The rate observed using the CMB differs from that calculated using Type Ia supernovae. Some scientists believe this inconsistency might indicate that only certain types of quintessence models are viable, possibly involving additional interactions between dark energy and other forces. Modifying gravity. Could it replace dark energy? An alternative approach to explaining cosmic acceleration involves modifying Einstein's theory of general relativity. Some modified gravity theories propose that the accelerated expansion of the universe might be a natural result of how gravity works on large scales, eliminating the need for dark energy altogether. However, a critical discovery in 2017, the measurement of gravitational waves from the GW 170817 event, ruled out many of these alternative theories, strengthening the case for dark energy as a genuine phenomenon. How dark energy took over the universe. Scientists estimate that the universe's expansion began accelerating around 5 billion years ago. Before this period, the gravitational pull of dark matter and regular matter was strong enough to slow the expansion. However, as the universe expanded, matter spread out and became less influential, while dark energy remained nearly constant. Eventually, dark energy's influence surpassed gravity, leading to the accelerated expansion we observe today. The ultimate fate of the universe, scenarios driven by dark energy. The fate of the universe depends largely on the nature of dark energy. 1. Endless expansion. If dark energy remains constant, as predicted by the cosmological constant model, the universe will continue expanding forever. Galaxies beyond our local group will drift away, eventually moving faster than the speed of light relative to us. These galaxies will fade from view, leaving an isolated, dark cosmos. 2. 3. The Big Rip. If dark energy increases over time, the universe could end in the Big Rip, where the force of expansion becomes so powerful that it destroys all structures, down to the atomic level. 4. 5. The Big Crunch. Alternatively, if dark energy reverses its effect, it could lead to a Big Crunch, where the universe's expansion halts and reverses, causing everything to collapse back into a singularity. 6. 7. Cyclic model. Some theories suggest the universe might undergo endless cycles of expansion and contraction, with each Big Bang followed by a Big Crunch. 8. Dark energy's role in the early universe and beyond. The timeline of the universe's history shows that dark energy was not always dominant. During the first few 100,000 years, matter and radiation shaped the cosmos. It was only after the formation of galaxies and large-scale structures that dark energy began to take over, accelerating the universe's expansion. Dark energy remains one of the greatest unsolved mysteries in physics. Its discovery has transformed our understanding of the cosmos, revealing that the universe is not just expanding but doing so at an ever-increasing rate. Whether dark energy is a fundamental aspect of space, a dynamic force like quintessence, or an indicator of new physics beyond our current theories, it continues to challenge and inspire cosmologists and physicists worldwide. As technology advances and new observational techniques are developed, the hope is that future discoveries will bring us closer to uncovering the true nature of dark energy. Whatever the answer, it promises to deepen our understanding of the universe and our place within it, opening new horizons for both science and human curiosity. The distant future, the end of the stelliferous era and the fate of the universe in the far reaches of time, the stelliferous era, the age of star formation, will eventually conclude. This will occur when the birth of new stars ceases, leaving the universe to continue its relentless expansion. As this expansion persists, only the galaxies closest to us will remain observable, with the rest receding beyond the cosmic horizon. The ultimate fate of the universe, a mystery yet to be solved. The destiny of the universe remains one of the most profound mysteries in cosmology, with several potential scenarios still under consideration. By studying the current state of the cosmos, scientists hope to better predict its future. The observable expansion of the universe led to the formulation of the Big Bang theory, which proposes that the cosmos originated from an extremely hot and dense state. The lambda CDM model, the leading explanation and enhanced version of the Big Bang theory, known as the lambda cold dark matter, lambda CDM, model, aligns closely with a broad spectrum of astrophysical observations. This model traces the universe's expansion backward to incredibly high temperatures and densities. However, as we approach the earliest moments, where temperatures and densities become infinite, current physical models break down. The limitations of current models, the breakdown at infinite temperature. When tracing cosmic expansion backward, we encounter a point where temperature becomes infinite, or the scale factor approaches zero, effectively marking the beginning of time. At this juncture, our physical theories cease to be applicable. This paradox indicates that postulating an initial gravitational singularity is beyond the scope of present-day physics. The Planck epoch, where physics breaks down according to the standard cosmological model, the universe has been expanding since it was in an extremely hot state. When we trace this expansion back to the Planck length, a minuscule distance where quantum effects dominate, the familiar laws of physics lose their validity. In this realm, energy levels become so extreme that quantum gravitational effects override Einstein's equations of general relativity. The Grand Unification epoch, a time of immense heat and energy following the Planck era, the universe may be modeled using extensions of the standard model of particle physics, such as Grand Unified Theories, GUTS. However, no GUT has yet matched current observations. In the first septosecond to rontosecond after the Big Bang, the universe experienced the Grand Unification epoch, marked by temperatures exceeding quadrillion gigaelectron volts. Cosmic inflation, the universe's rapid expansion. One of the most crucial phases in the universe's development was cosmic inflation, a rapid expansion that occurred between 10⁻33 10⁻33 and 10⁻32 10⁻32 seconds after the Big Bang. During this fraction of a second, the universe expanded by at least a sextillion times its original size, smoothing out any irregularities and laying the foundation for the large-scale structures we observe today. The mystery of cosmic inflation, the driving force behind this dramatic expansion, is not yet fully understood. A popular hypothesis suggests that inflation began when the strong nuclear force separated from the electroweak force, creating a field known as the inflaton field. This field generated a repulsive force, causing the universe to expand at a phenomenal rate. Reheating, the universe gets hot again at the end of inflation. The inflaton field released its energy, a process known as reheating. This released an immense amount of heat, filling the universe with a dense plasma of particles, including quarks, antiquarks, and gluons. Some models suggest that this marked the start of the electroweak epoch, though other theories like warm inflation propose a more gradual transition. Electroweak symmetry breaking, particles gain mass about 10⁻12 10⁻12 seconds after the Big Bang, at temperatures around 1.5 TeV, a pivotal event known as electroweak symmetry breaking occurred. During this phase, the Higgs mechanism gave mass to elementary particles. Simultaneously, the weak nuclear force and electromagnetic force began to act differently. W and Z bosons gained mass, restricting the weak nuclear force to short distances. Photons remained massless, allowing the electromagnetic force to act over vast distances. The formation of fundamental forces after this key transformation, the four fundamental forces of nature, gravity, electromagnetism, weak nuclear force, and strong nuclear force, emerged in the forms we recognize today. However, the temperature remained too high for stable atomic structures to form, preventing the existence of protons, neutrons, or atoms. The quark epoch, a seething plasma of particles following electroweak symmetry breaking, the universe entered the quark epoch, around 10-12 10^-12 to 10-5 10^-5 seconds after the Big Bang. During this phase, the universe was a hot, dense plasma of quarks, gluons, leptons, and antiparticles. The energy from their collisions was so intense that quarks could not combine to form protons or neutrons. Baryogenesis, matter's victory over antimatter during the quark epoch, a mysterious imbalance occurred, favoring baryons, particles like protons and neutrons, over antibaryons. The reason for this asymmetry remains unknown, but without it, matter would have annihilated with antimatter, leaving behind a universe filled with radiation. Nucleosynthesis, the formation of light elements approximately 2 to 20 minutes after the Big Bang, the universe cooled enough for protons and neutrons to combine into the first atomic nuclei. This period of Big Bang nucleosynthesis produced light elements, including deuterium, heavy hydrogen, helium-4, making up about 25% of the universe's mass, trace amounts of lithium and beryllium. The observed abundances of these light elements today strongly support the Big Bang model. The cosmic dark ages, waiting for the first stars for the next 370,000 years, the universe was a dark, opaque plasma of electrons, protons, and photons. During this period, light was constantly scattered, preventing it from traveling freely. This era, known as the cosmic dark ages, ended with recombination, when electrons combined with protons to form neutral hydrogen atoms, allowing light to travel unimpeded. The cosmic microwave background, the oldest light the photons released during recombination, became the cosmic microwave background (CMB), the oldest light in the universe. This afterglow of the Big Bang continues to provide a snapshot of the universe as it was just 380,000 years after its birth. The end of the stelliferous era and beyond. As the universe continues to expand, star formation will eventually cease, marking the end of the stelliferous era. What follows depends on the nature of dark energy and the universe's ultimate fate. Possibilities include the Big Freeze, eternal expansion leading to a cold, dark, and dilute universe. The Big Rip, an accelerated expansion tearing apart galaxies, stars, and even atoms. The Big Crunch, a reversal of expansion, collapsing the universe back into a singularity. The Big Bounce, a cyclic model where the universe expands, contracts, and then rebounds in a new Big Bang. Conclusion: the unfinished story of the cosmos. The universe's fate remains one of the most compelling mysteries in modern science. As we continue to explore the cosmos, each discovery brings us closer to understanding our place within this grand cosmic narrative. Whether the future holds a cold void, a cataclysmic rip, or an eternal cycle, the story of the universe is far from over. In the early universe, dark matter didn't form dense objects like stars or planets. Instead, it gathered into vast, thin filaments and halos. Unlike regular matter, dark matter cannot lose energy by emitting radiation, which prevents it from collapsing into compact structures. Regular matter, on the other hand, can release energy through radiation, allowing it to condense into denser forms such as stars and gas clouds. Around 370,000 years after the Big Bang, two significant events took place: recombination and photon decoupling. During recombination, ionized particles like electrons and protons combined to form the first neutral atoms. Photon decoupling occurred when photons, previously trapped by constant interactions with charged particles, were finally able to travel freely as atoms reached stable energy states. Before recombination, the universe was incredibly hot and filled with ionized plasma. Photons constantly collided with charged particles, preventing light from traveling far and rendering the universe opaque, almost like a cosmic fog. While light existed, it couldn't penetrate the dense plasma to create a clear view of the cosmos. As the universe continued to cool, starting around 18,000 years after the Big Bang, electrons began to bind with helium nuclei, leading to the formation of neutral helium atoms. By about 100,000 years, neutral hydrogen atoms began to appear as well. This initial combination of electrons and nuclei, referred to as recombination, wasn't a process but rather the first instance of these particles coming together. Approximately 100,000 years later, the universe had cooled enough for the first molecule, helium hydride, to form. This molecule played a crucial role in early molecular chemistry. In 2019, scientists confirmed the existence of helium hydride in space within the planetary nebula NGC 7027. This molecule eventually reacted with atomic hydrogen, leading to the creation of molecular hydrogen, the essential component for star formation. When hydrogen atoms combined in their low-energy state, they weren't very efficient. Typically, they held on to their high-energy electrons, and as they combined, these electrons would release energy, dropping to lower energy states and emitting photons in the process. This release of photons is known as photon decoupling. While some of these photons were absorbed by other hydrogen atoms, many remained free. By the time recombination concluded, most protons in the universe had combined with electrons to create neutral hydrogen atoms. This transition significantly increased the distance photons could travel without being absorbed, making the universe transparent to light, radio waves, and other electromagnetic radiation for the first time. The photons released during this era had a temperature of around 4000 K, which to the human eye would have appeared as a soft white light with a warm yellow or orange hue. Over billions of years, as the universe expanded, these photons stretched into longer wavelengths, transitioning from visible light to microwave radiation at about 2.7 K. This process, called redshifting, is due to the universe's expansion, which elongates photon wavelengths and reduces their frequency. These redshifted photons are still detectable today as radio waves, contributing to what we know as the cosmic microwave background, CMB. The CMB offers a valuable glimpse into the early universe, preserving evidence of its development and the conditions shortly after the Big Bang. Around the same period as recombination, pressure waves within the electron-baryon plasma became embedded in the universe's matter distribution as it began to condense. These pressure waves, known as baryon acoustic oscillations, left behind subtle patterns in the large-scale structure of the cosmos. The cosmic microwave background serves as a snapshot of the universe at the end of this era, showcasing the slight fluctuations present from the earliest moments of cosmic inflation. The distribution of galaxies observed today reflects the universe's scale and evolution over time. Despite the universe becoming transparent following recombination and decoupling, it remained too cool for stars or galaxies to form immediately. It wasn't until gravity began to pull together denser regions of gas, over hundreds of millions of years, that stars and galaxies started to emerge. This delay explains why stars only began shining long after recombination. The universe entered a phase known as the Dark Ages around 370,000 years after the Big Bang. During this time, temperatures dropped from approximately 4000 K to 60 K. The only photon sources were those emitted during recombination, which we now observe as the CMB, and photons sporadically released by neutral hydrogen atoms through a process known as the 21 cm spin line, which falls within the microwave frequency range. Within just 3 million years, the CMB photons had shifted out of visible light into the infrared spectrum. For a long period, the universe remained without visible light, experiencing true darkness until the first stars ignited. These early stars, known as population 3 stars, began to form a few hundred million years after the Big Bang, casting the first visible light and signaling the end of the Dark Ages. As structures gradually took shape, early galaxies started to appear between 180 and 700 million years after the Big Bang. This slow evolution continued, and by approximately 1 billion years after the Big Bang, the universe began to resemble its current state. The oldest stars and galaxies observed today formed just after the onset of reionization, a process that began around 400 million years post-Big Bang. In 2016, the Hubble Space Telescope observed galaxies like GN-Z11, dating to about 400 million years after the Big Bang. The more advanced James Webb Space Telescope, launched in December 2021, can detect galaxies up to 100 times fainter than Hubble, potentially revealing objects from as early as 180 million years post-Big Bang, possibly even earlier than the first galaxies. Scientists are also investigating a faint form of radiation known as the 21 cm spin-line radiation, which may offer deeper insights into the early universe than the CMB. By studying this radiation, researchers hope to refine our understanding of when the first stars, galaxies, black holes, and quasars emerged and to pinpoint the precise timing of the reionization period. Overall, our understanding of the universe's early stages continues to evolve with new discoveries and technologies. Each finding helps piece together the vast and complex puzzle of how the cosmos transformed from a dark and featureless expanse into the vibrant and dynamic universe we see today. In 1947, Dutch physicists Hendrik Casimir and Dirk Polder conducted a groundbreaking experiment that led to the discovery of what is now known as the Casimir effect. They placed two uncharged metal plates extremely close together inside a vacuum. According to classical physics, nothing significant should have occurred. However, to their astonishment, the plates mysteriously moved toward each other, as if an invisible force was drawing them together. The cause of this force was traced to quantum fluctuations. The narrow space between the plates was so small that certain quantum energy fluctuations were suppressed, leading to an imbalance in pressure between the inside and the outside of the plates. This imbalance created an attractive force, demonstrating that even in a vacuum, there is something present, something invisible yet undeniably real. The Casimir effect was revolutionary because it provided concrete evidence that empty space is far from empty. It confirmed that the vacuum itself contains energy, fundamentally altering our understanding of physics and the nature of reality. But this discovery raised even more profound questions. If empty space is filled with quantum fluctuations, could these tiny bursts of energy have played a role in the creation of the universe itself? Many scientists believe they did. According to some of the most compelling theories in cosmology, the universe might have sprung into existence due to quantum fluctuations in a primordial vacuum. In essence, what we perceive as nothing could have been a seething sea of quantum energy. Under the right conditions, one of these fluctuations could have expanded exponentially, triggering what we now call the Big Bang. This idea aligns with modern quantum field theory and cosmic inflation, suggesting that the universe was born not from absolute nothingness but from a state where energy was already bubbling beneath the surface. The discovery of quantum fluctuations challenges our deepest assumptions about the nature of reality. It implies that even in the vast emptiness of space, there is an invisible, restless energy at work, one that may hold the key to the greatest questions about existence itself. Could the universe be just one of countless fluctuations emerging and dissolving in an infinite cosmic cycle? Could quantum mechanics reveal deeper layers of reality that we have yet to comprehend? These are the kinds of questions that continue to fascinate physicists as each new discovery peels back another layer of the universe's most profound secrets. The idea that something could come from nothing through quantum fluctuations may seem bizarre, but it is a crucial concept in understanding the workings of the universe. In quantum field theory, the vacuum is not merely empty space. It is more like a bubbling energetic sea of potential. This hidden energy can spontaneously create and destroy particles in an instant. These fleeting entities, known as virtual particles, don't last long, but their brief existence has real, observable effects. One example is the Casimir effect itself, where even the smallest quantum fluctuations result in real physical consequences, like attracting two uncharged metal plates that aren't physically touching. These seemingly insignificant fluctuations can have a massive impact over time, especially at the smallest scales of reality. In the early stages of the universe, just moments after the Big Bang, quantum fluctuations may have played a pivotal role in shaping everything we see today. During this period of extreme heat and energy, these fluctuations acted like tiny seeds planted in the very fabric of the cosmos. Initially invisible, These seeds gradually grew into the massive structures we now recognize as galaxies, stars, and even the enormous cosmic web that stretches across the universe. This idea is supported by the theory of cosmic inflation, which proposes that the universe underwent an extremely rapid expansion just moments after the Big Bang. During this intense and brief period, quantum fluctuations were stretched across vast regions of space. These fluctuations left behind tiny variations in density, which over billions of years evolved into the stars, galaxies, and clusters we observe today. Quantum fluctuations were not just random, insignificant events, they may have been the mechanism that allowed the universe to evolve from a nearly featureless state into the structured cosmos we see now. In essence, these microscopic fluctuations in the quantum field set the stage for the formation of everything around us, from galaxies and stars to planets and even life itself. The implications go even further. Some scientists suggest that the entire universe could have emerged from a quantum fluctuation. In this scenario, the universe didn't require a pre-existing cause or creator to come into being. Instead, it could have spontaneously arisen from the quantum vacuum itself. This challenges conventional notions of cause and effect, proposing that creation can happen without a cause, and that particles, and even entire universes, can pop into existence from what we perceive as nothing. This revolutionary idea proposes that the universe might have emerged from a quantum fluctuation in an energetic vacuum, rather than from an event like the Big Bang emerging from a pre-existing state. It redefines our understanding of nothingness, revealing that what we see as empty space is actually a dynamic, energetic playground where creation is constantly happening. This interpretation not only pushes the boundaries of our understanding of existence but also offers a radically different perspective on the origins of the cosmos. The notion that our universe could have come into existence from a tiny, almost invisible fluctuation in quantum energy is both profound and mind-bending. It suggests that creation is not a one-time event but a continuous process occurring in the quantum world. As we explore these concepts, we confront age-old philosophical questions about existence itself. Quantum mechanics, which governs the behavior of the smallest particles of matter, challenges our everyday understanding of the world by suggesting that nothingness is not an empty void but a fertile ground filled with potential. It is a space where the tiniest fluctuations can grow into something immense, perhaps even into universes like our own. In this light, the birth of our universe is no longer viewed as an isolated event that happened long ago. Instead, it is part of a continuous cycle of creation and destruction occurring in the quantum realm. Here, the line between nothing and something is blurred, revealing that even empty space can be full of untapped energy, ready to give rise to new worlds when the right conditions align. The Casimir effect and the concept of quantum fluctuations have reshaped our understanding of the cosmos. They suggest that creation is a constant, ongoing process happening even in the so-called emptiness of space. And in this sense, the question of how something can come from nothing may not be a paradox after all. Instead, it may be the very nature of existence itself. Earth's atmosphere is crucial for maintaining conditions suitable for life. Without it, the planet would be exposed to the harsh realities of space, including harmful solar radiation and extreme temperature fluctuations. The atmosphere not only shields Earth from damaging cosmic rays but also helps regulate temperature, ensuring a stable climate where life can thrive. Complementing the atmosphere, Earth possesses a magnetic field, generated by the movement of molten iron within its core. This magnetic shield plays a vital role in protecting the planet from solar winds, powerful streams of charged particles emitted by the sun. These solar winds have the potential to strip away a planet's atmosphere over time, as observed on Mars. Without this magnetic defense, Earth would likely face a similar fate, leaving it barren and inhospitable to life. Another unique characteristic that sets Earth apart is the abundance of water. Known as the Blue Planet because over 70% of its surface is covered by oceans, Earth is the only known planet in our solar system where liquid water exists in such vast quantities. Water is essential for all known life forms, from the simplest microorganisms to the most complex animals. It sustains life, aids in nutrient transport, and helps regulate the planet's temperature, making Earth an ideal environment for life to flourish. Earth's habitability is also heavily influenced by geological activity, specifically the movement of tectonic plates. These plates are constantly shifting, which recycles nutrients and regulates the planet's temperature. This dynamic process, known as plate tectonics, maintains Earth's long-term climate stability, creating conditions favorable for life to thrive over billions of years. The movement of tectonic plates also leads to the formation of mountain ranges, earthquakes, and volcanic activity, contributing to the planet's ever-changing landscape. But how did Earth and the other planets in our solar system form in the first place? To answer this, scientists look to planetary formation theories, which explore how planets are born from the dust and gas of the early solar system. One of the most widely accepted explanations is the nebular hypothesis. This theory proposes that planets are formed from the leftover materials surrounding a newly born star. According to the nebular hypothesis, a star forms within a massive cloud of gas and dust called a nebula. After the star ignites at its core, the remaining gas and dust orbiting it form a rotating disk known as a protoplanetary disk. Within this disk, tiny particles of dust and ice collide and stick together, gradually forming larger chunks known as planetesimals. Over millions of years, these planetesimals continue to collide and merge, eventually forming larger bodies called protoplanets. Through a process known as accretion, these protoplanets gather more material, growing into fully developed planets. This process explains how rocky planets like Earth and Mars formed closer to the Sun, where temperatures were high enough to prevent gases from condensing. In contrast, gas giants like Jupiter and Saturn formed farther from the Sun, where temperatures were cooler and gas was abundant. These gas giants began as solid cores but eventually attracted vast amounts of surrounding gas, forming their thick atmospheres. Two main theories explain the formation of gas giants: core accretion and disk instability. In the core accretion model, a solid core gradually collects surrounding gas over time, forming a massive planet. This model works best for planets forming far from their star, where more gas is available. On the other hand, the disk instability model suggests that gas giants form rapidly when regions of a protoplanetary disk collapse under their own gravity. This rapid formation could explain how Jupiter formed quickly enough to influence the structure of our solar system. Modern telescopes like the James Webb Space Telescope and the Atacama Large Millimeter Array allow scientists to observe the formation of planets in distant star systems, confirming that the processes that shaped our solar system are happening throughout the universe. These observations reveal protoplanetary disks around young stars where planetesimals collide and merge to form new planets, showing that our solar system's formation is part of a universal phenomenon. The birth of our solar system was chaotic, a swirling cloud of gas and dust collapsing under gravity, igniting the sun, and forming planets through countless collisions. Over billions of years, the planets settled into stable orbits, each unique in composition and characteristics. Among them, Earth emerged as the only planet known to support life, thanks to a perfect combination of distance from the sun, presence of water, a protective atmosphere, and a magnetic field. This leads to one of the most profound questions humanity has ever faced: are we alone in the universe? With countless planets orbiting distant stars, could there be other worlds capable of supporting life? This mystery drives the search for extraterrestrial life, pushing scientists to study exoplanets and explore the conditions necessary for life to exist. One of the most crucial requirements for life, as we know it, is liquid water. Earth's position in the habitable zone around the Sun allows water to exist as a liquid, a solid, and a gas. This Goldilocks zone is not too hot or too cold, creating an environment suitable for life. Planets too close to their stars, like Venus, are too hot, while those too far away, like Mars, are too cold. Earth's perfect positioning enables water to flow as rivers, fill oceans, and support a rich diversity of life. Life also requires a stable energy source. On Earth, most life depends on energy from the sun. Plants convert sunlight into chemical energy through photosynthesis, supporting the entire food chain. However, the discovery of life around hydrothermal vents on the ocean floor revealed that life can also thrive without sunlight, relying instead on heat and chemicals from the Earth's core. This raises exciting possibilities for life in extreme environments on other planets or moons, such as Europa, a moon of Jupiter, or Enceladus, a moon of Saturn, where subsurface oceans could provide similar conditions. For life to evolve, a planet must maintain stable conditions over long periods. Earth's atmosphere and magnetic field play crucial roles in protecting life from cosmic radiation and maintaining temperature balance. Without them, Earth would be a cold, lifeless rock. This raises the question, are there other planets with similar protective features? This is where the Drake equation comes into play. Formulated by astronomer Frank Drake in 1961, this equation estimates the number of civilizations in our galaxy capable of communication. It considers factors like the number of stars with planets, the likelihood of life developing, and the chances of intelligent civilizations evolving. Although it doesn't provide a precise answer, it serves as a framework for organizing the search for extraterrestrial intelligence. Yet, this search raises the Fermi paradox, named after physicist Enrico Fermi, who asked, "Where is everybody?" If the universe is so vast and life is likely to exist elsewhere, why haven't we detected any signals from intelligent civilizations? The paradox suggests many possible explanations, from the rarity of intelligent life to civilizations destroying themselves before reaching advanced communication stages. It could also be that other civilizations are avoiding contact or that the vast distances make communication impossible. Despite these challenges, the search continues, driven by curiosity and the possibility of a groundbreaking discovery. Using radio telescopes to listen for signals and exploring distant exoplanets, scientists hope to find evidence that we are not alone. The discovery of intelligent extraterrestrial life would redefine humanity's understanding of its place in the cosmos. In this cosmic journey, Earth stands as a unique, life-supporting planet, shaped by complex processes of planetary formation and geological activity. But with billions of stars and countless planets scattered across the universe, the possibility of other life-bearing worlds remains an open and tantalizing question, one that humanity continues to explore with an insatiable curiosity. The universe's fate is a subject of great intrigue and speculation. Among the many theories, one suggests a future where the universe reverses its expansion, contracting back to a state of infinite density and heat, possibly leading to the birth of a new universe. This concept, known as the Big Crunch, envisions a cosmic cycle of creation and destruction, where the universe collapses only to be reborn in another Big Bang. This idea paints a picture of an eternal cosmic cycle but remains speculative, especially in light of current observations showing the universe's expansion is accelerating, not slowing down. Several scenarios have been proposed to explain how the universe might end: the Big Freeze, the Big Rip, and the Big Crunch. Each possibility depends on the nature of dark energy, a mysterious force driving the universe's accelerated expansion. The big question is how dark energy will behave in the future. Will it continue to push the universe apart, grow stronger over time, or eventually fade, allowing gravity to pull everything back together? The Big Freeze suggests that if dark energy remains constant, the universe will expand forever, cooling down as galaxies drift apart, stars burn out, and black holes evaporate, leading to a cold, dark, and empty cosmos. In contrast, the Big Rip posits that if dark energy grows stronger, it could eventually tear galaxies, stars, planets, and even atoms apart, ending the universe in a violent disintegration. The Big Crunch imagines a scenario where dark energy weakens over time, allowing gravity to reverse the expansion and pull everything back into a dense singularity, potentially triggering a new Big Bang. The discovery of dark energy in 1998 revolutionized our understanding of the universe's future. Initially, astronomers expected gravity to slow down the cosmic expansion. However, observations revealed that the universe is expanding faster and faster, implying the existence of an unknown force, dark energy, making up about 68% of the universe. Yet, despite its dominance, its true nature remains a mystery. One possibility is that dark energy is a cosmological constant, a fixed energy inherent to empty space, unchanging over time. This would lead to an ever-expanding universe gradually cooling into a big freeze. Alternatively, dark energy could be dynamic, varying over time. If it grows stronger, it could cause the Big Rip, a scenario where everything from galaxies to atoms is torn apart. Understanding what dark energy is remains one of the greatest challenges in modern physics, as it holds the key to the universe's ultimate fate. While these cosmic fates concern the distant future, individual stars, galaxies, and black holes will experience their own ends long before the universe itself concludes. The life cycles of these celestial objects shape the evolution of the cosmos. Stars, for example, are born, live, and die in spectacular ways, influencing the universe's structure and composition. Stars, the luminous beacons of the cosmos, have finite lifespans determined by their mass. Smaller stars, like red dwarfs, burn their fuel slowly, living for trillions of years before fading into black dwarfs, cold, dark remnants that emit no light. These stars are expected to outlast all others, lingering as the last sources of faint light in a dark universe. Medium-sized stars, like the Sun, expand into red giants as they exhaust their nuclear fuel, shedding their outer layers to form beautiful glowing nebulae. What remains is a white dwarf, an incredibly dense core that slowly cools over billions of years. Eventually, it will become a black dwarf, radiating no heat or light. The most massive stars end their lives in spectacular supernova explosions, outshining entire galaxies for brief moments. These powerful blasts leave behind either a neutron star or a black hole. Neutron stars are incredibly dense remnants, while black holes are regions of space where gravity is so strong that nothing, not even light, can escape. Yet, even black holes are not eternal. Through a process called Hawking radiation, black holes slowly lose mass and energy over unimaginable timescales. Eventually, they evaporate entirely, leaving behind nothing but empty space. This slow evaporation suggests that even the most massive objects will one day disappear, contributing to the Big Freeze scenario. As the universe continues to expand, galaxies will drift farther apart, growing isolated in an ever larger, emptier cosmos. Some galaxies will merge, forming massive elliptical galaxies, but over time, star formation will cease as gas reserves are depleted. Without new stars to illuminate them, galaxies will gradually darken, and their light will fade, leading to a universe filled with cold, dark remnants of once brilliant celestial structures. This darkening future ties into the Big Freeze, where the cosmos becomes a vast, cold void with no new sources of energy. However, if dark energy grows stronger, the Big Rip could occur, tearing galaxies, stars, planets, and even atoms apart, ending the universe in a cataclysmic rupture. Conversely, if dark energy weakens, the Big Crunch could collapse the cosmos back into a singularity, possibly rebirthing a new universe. The universe, vast and magnificent, is a temporary spectacle. Its beginning was marked by the explosive birth of space, time, and matter, and its end, whether through freezing, ripping, or collapsing, will be equally dramatic. Yet, this end is not expected for trillions of years, giving humanity a fleeting but precious moment to explore, learn, and marvel at the cosmos. The ultimate fate of the universe remains one of the most profound mysteries of existence. Whether it ends in cold darkness, cataclysmic destruction, or a rebirth in a new Big Bang, the universe's story will have a final chapter. However, for now, it continues to expand, filled with stars, galaxies, and the possibility of life. At the core of this cosmic narrative lies a philosophical question: why does the universe exist at all? Some argue that the universe must have a cause beyond the physical world, leading to the cosmological argument, which posits that everything must have an origin. Others suggest the universe is a brute fact, something that simply exists without explanation. This philosophical debate connects to the distinction between contingent and necessary existence. A contingent thing could have been different or not existed at all, like Earth or the Sun. Some philosophers propose that the universe and its laws might be necessary, existing by default. Others argue that the universe is contingent, raising the possibility that there was once nothing. Could the universe have emerged from nothing? Quantum mechanics suggests that this is possible. In the quantum world, particles can spontaneously appear and vanish, seemingly from nothing. Some physicists propose that the universe itself could have emerged from a quantum fluctuation, arising from a state of quantum nothingness. In this view, the universe is one of countless fluctuations in an infinite quantum sea, each giving birth to its own cosmos. This idea challenges traditional notions of cause and effect, suggesting that existence itself is a product of randomness and probability. It also raises questions about the nature of time, space, and reality, pushing the boundaries of human understanding. The universe's story, from its explosive birth to its distant death, invites us to contemplate our place within this cosmic tapestry. It inspires awe and curiosity, driving humanity's quest for knowledge. And while the ultimate fate of the universe remains unknown, the journey to understand it continues, revealing the beauty and mystery of existence itself.